Hi, this is the fourth video in my Yocto Linux video series, and in this video I want to go over the process to create a kernel device driver. As I did in the previous video, number 3, instead of going straight for the kernel module running on the development board, I'm going to first practice writing the kernel on my host, or my VM system here, my Linux system. To get started, I want to try to find the Linux kernel module documentation project's overview of how to do a Linux kernel device. And looks like we're looking for TDLP or TLDP, and we want to make sure we're on version 2.6. The kernel went through a significant change in the way modules are handled between version 2.4 and 2.6. To make a kernel device driver that handles character operations, we have to implement ourselves as a character device driver, and to do that we have to pass a structure to the kernel that's going to tell it how or what functions of ours to call in response to events from the user program. If the user program, for instance, were to call open, it's going to need to know what function of ours to call in response to that. The same thing would be true for read, for write, as well as release. So in the previous video we made our little hello kernel module, and I'm going to modify this hello kernel module now to implement one of these file operations. And if I scroll down just a little bit, we can actually just kind of copy and paste this structure initialization. So in this struct file operations fops, essentially we're using the name of the field of the struct with the name of a function. I haven't written these functions yet. I'm going to rename these here to be hello read, hello write, hello open, and hello release. So these file operations are going to connect what happens on the event side to the code that I'm going to write. I also need to make these functions, and so for instance, to have a function that handles read, we can copy the signature from that struct over here, and so my function read, which I'm calling hello read, needs to return a size t. It needs to take a file pointer. It needs to take a output buffer. It needs to have a number of bytes, and it needs to have an offset. In the case of a write, now this pointer here is inside the parentheses, which means it's looking for a file pointer or a function pointer. So I'm going to disregard that. We're going to have the function here called hello write, and it's going to take a file p. And this pointer is marked as constant. We're not going to change this because when the user is writing to our program, we're handling the write. So as far as my kernel driver is concerned, these are input bytes, and we're going to have some number of bytes at some offset. And then I need to have my hello open. Oops, sorry, it needs to be inode p, and this will be file p, and then finally we're going to have our close. So at this point, these functions match the names that are going to be stored in this file operations, and we can kind of scroll down just a little bit through this documentation page, and here we see how to register the device that we want to create. And so we're going to do this during initialization. So here during the program initialization, I want to call register churdev, and I can either fill in a major number, and if you've never understood major numbers before, hang on, I'll explain it in just a minute. So I can request one, or I can leave it as 0 and it will be filled in for me. And then I give it a name for the module, and the name for this module is hello, and the file ops is this fops that we just created here. So this is the function that we're going to call. We're going to So what's going to happen is we're going to create the device, and we're going to register ourselves, and I'm going to let Linux pick a device number for me, and I'm going to display the message whatever that major number is. When we're all done and we want to unregister ourselves, we can handle that if we wanted to, but at this point I'm not going to worry about it so much. This file structure is actually going to be found in an include file, and I need to make sure that I have that. And if I were to scroll down here just a little bit, we can see the example that they're giving. So this is the initialization module, and here's how they're handling device open. And in the case of device open, we can only open it once. So I'm going to keep track of, I'm kind of making my own up as we go here. We're going to keep track of whether we're open or not. So that's volatile static int is open, initially is 0, and if is open is equal to 1, then we're going to return negative e busy. Probably should print a little bit of an error message as well. So we're going to print k, no, we're not printf, current info error, hello device already open. Otherwise, we're going to open it. It's been a long day, can't type. In the case of close, if is open is equal to 0, and we can't really have anything going on there, so can't close a device that we haven't opened. Otherwise, we'll keep track of that it's not been opened. In their example from the Linux documentation project, they use try module get and try module put. These are atomic operations that increment the use count of a module. If you were to try to remove a module that has a usage count, you won't be able to because the module has been used. So for example, we could in our open do the same thing. And say here that try module get this module, and then here module put. And so this will just prevent the module from being unloaded while somebody's waiting for it. Alright, here we are in the device read, and here's our file pointer, the buffer that we're going to fill, because remember we're handling a read, so for the kernel's perspective a read is actually a write. The length of the buffer that we've been asked to fill, and the offset from where we're going to start to read. And so if we look at what their documentation is saying, we're going to try to fill as many bytes as we can into this buffer, and then they do this weird pointer arithmetic right here, where what they're trying to do is they're using this put user function which copies bytes into a user memory from kernel memory. So the problem is that kernel memory and user memory are in different virtual pages, and we need to make sure that we can bypass any MMU security safely, and that we're not going to have a problem, because remember the kernel could theoretically dump data anywhere in the system. So this put user function is a kind of a safety to make sure that we don't leak memory into improper processes or overwrite other kernel structures. If we just follow along with their little example here, what I can do is let's see, when we first create the device here in hello start, what we can do is do an strn copy into that, what did I just call it? I called it message. Oh my. So we can strn copy into message the message hello world. And then really if we were smart we'd even do, well, we shouldn't have to worry about that. And then num bytes will be equal to the length of the message. So this is the original message. If you are reading from me, I'm going to copy these bytes into your message up to the length of the number of bytes. Okay? And so here we are in the reader, and what we're going to do is we're going to keep track of the number of bytes that we've already read, and we're going to follow along with what their example here was. We're going to look to see if the pointer was equal to, or if the character at the message pointer was equal to null. And so I'm not a big fan of the way that they've done this. Really what we're after is we have an offset value here, and so if the offset, first of all, if the offset's null, that's going to be a problem. Return a negative none. If the offset is equal to, or is greater than or equal to the number of bytes, then return 0. So if you've already read to the end of the string, then there's nothing left to read. Otherwise, let's see, while offset is less than num bytes. So this is where, so we're going to use the offset of wherever you were when you read, and we're going to keep track of where we are in the message. We also need to keep track of where we are in that number of bytes. So while bytes read is less than n bytes, and the offset is less than the number of available bytes, then we can do put user into the source is going to be our message of offset, and we're going to put that into the user's output buffer. Of bytes read. You know, this pointer arithmetic down here, I'm sure people are screaming at me, this is, you know, so cool looking. I really do like the array notation better. I think it's a little bit easier to see what's going on. At this point, offset goes up by 1, bytes read goes up by 1, and then I don't have to mess around with changing the pointer where they start. We'll just use the array notation. And honestly, the compiler is going to compile away this pointer arithmetic anyway. Okay, so at the very end, we can then have hello read return the number of bytes read. And so that kind of follows along with their example here. For their example write, so if you try to write to my module at this point, we're going to just return that einval like they do here. And maybe that's what we can do here for invalid value. And so at this point, we're actually ready to make. And we get some errors and warnings here, and so we want to make sure that we fix these. My experience with the kernel and my recommendation is warnings are never warnings when you're dealing with kernel code. Wow, that was a struggle. We've got the kernel module load. I can only tell you from practical experience that if you're using a virtual machine, this is the point where you want to go ahead and take a snapshot, and we'll just call it snapshot 6, because if this fails, I want to be able to revert back to right now. I'm going to go ahead and insmod sudo insmod hello.ko. And I see here that the module loaded, and it's module number 245. And the way that this all works is, it might be better if I go over to my whiteboard. All right, so what I want to do is just review a little bit about the relationship between the kernel and the user code. And so the first thing we can kind of do is divide the world up into two parts. We have the user land and we have kernel land. I know that seems kind of silly, but there it is. And there's an entry point here on the kernel side for character devices. Just like there's another kernel entry point here for block devices. Block devices are things like your hard drive. Character devices are things like your keyboard or your mouse. I'm really not a good artist. That's a mouse. The idea here, our character device drivers allow us to transfer bytes at a time. And what's going to happen is when we register a module, we're registering our hello module. And we're registering it as a character device. And part of what that means is there's an API. And the character... Sorry about that. Whoa. The character API has things like open and release, which is our close function, as well as read and write. And there's a whole pile of different character devices, and we're going to pick, say, one of them. So we might be number 254, whereas the keyboard might be 36 and the mouse might be 43. Those numbers are kind of at random. I don't know what their real numbers are. Over on the user side, we have access to do things like open and close and read and write in our programs. And all of this is going to be translated into system calls. And if I were to do this on a regular file, then what's going to happen is when I open, read, or write a file, that would actually go to yet a different interface. So on a regular file, like readme.txt, that goes down to the file system interface. Whoa. But there are a bunch of special versions of these things that are called special files. And a special file is a file that when I read from it or write to it, it's going to go to either the raw device driver. So for example, I can have a special file called tty, and it's going to have a connection to the terminal through the same major device number that it occupies over here on the kernel side. And I could have a device called mouse that occupies a major number 43, and that would read and write to the mouse. We're going to make another special file called hello that's going to be connected to device number 254. And as long as these match, then if I open, close, read, or write one of these special files, it will go to the character device, and the character device will look at the major number that I operated on and send it to the appropriate device driver to handle it. So the trick that we have to answer is, how do we make one of these devices? And the answer is going to be, we're going to do a make node command, and that make node command, whoops, the make node command, come on, is a command that we can run as root. We're going to have to be sudo for this, and we're going to give it the name of the file that we want to create, and that can be anywhere in the file system. Normally it's things like dev. The dev directory holds all of our device files kind of by through history. The type, C for character, B for block. The major number, in this case, will be 254, or whatever the major number is, and then a minor number that we can then pass along to the device driver. So for example, you might have multiple terminals hooked up to your machine. They might all share the same major number, but they'll have multiple minor numbers. The same is true for your block devices. I could have a major number that's more for my hard drives, and then that minor number, minor number 0 would be the first hard drive, minor number 1 would be the second hard drive. So that's the relationship between the device driver in the user space to the kernel mode device driver that handles it. We go through these special device drivers. This would be one of the entries in my device file system, and we see here is that C for character device, 7 for the major number, 128 for the minor number, and then the name is VCSA. The D message from when I loaded the kernel says I'm on device 245. I'm sorry, I thought it was 254. If I forget, there's a file called proc devices. If I read from this file, it shows me the character and the device special files, and 245, right there she is the hello driver. That's my driver. So as root, I can run the mknod command, and the mknod command allows me to create a special file. I give it a name, a type, a major, and a minor number. So I want to make it a character special, so a C, and I want to give it a name of hello, and we're going to do 245 and 0. Oh, the name comes first, sorry. Now, this file there's nothing special about putting device special files in the device directory or the dev directory. I'm choosing to create it here in the kernel folder that I'm working in. But at this point, for instance, I can cat hello. And when I read, so basically the cat command opens the file, reads the data until the end of file, and then closes the file. Let's do that strace command I love so much. And here we can see that it is, oh, I've got to find it. It's going to call open on the hello module, and because I have permission to do that, it'll open the module, and then it tries to read the data, and then it prints it out. There's nothing else there to read, and then it closes the file. And so I can read from that file as many times as I want. Now, I want to make some changes to this module. I want to be able to change the message that's displayed. So we're going to do a sudo rmmod hello. And now if I do an lsmod, I see a grep for hello. That's gone. And if I were to try to run this program again, the cat command, there is no device module there, and so I get an error. Okay, let's take a look at our hello.c file. And this time, when we do our write command, instead of saying that we can't handle a write, I want to kind of do the same thing that I did here. We're going to keep track of bytes, write, I guess, bytes written. And we're going to be looking at offset, and if it's null, return negative val. If offset is greater than or equal to 1023, then return negative val. So we can't overflow the size of our buffer. And then while bytes write is less than n bytes, and offset is less than 1023. In this case, I want to be able to, instead of doing a put user, I'm going to want to do a get user, and I need to have this go to my message at offset, and it's going to come from in pointer and then we can do our offset equals offset +1 and bytes write ++. And it might not be a bad idea to print k kern info the message as a result of writing to it. So once again, oh geez, we'll do our make, and we'll have to go ahead and do some debugging here. And theoretically now, I should be able to do my insmod on hello. Oh, one thing we want to go back and probably do if I'm really new to this is to basically take another snapshot. The reason for this is you're writing code in the kernel, and if you hose it, you're going to hose your kernel, and then you could lose data. Alright, so now I can do my insmod hello.ko. Gotta be sudo. And if I if I do my dmessage, oh, bad news. So somewhere we actually had something throw an error. Hope that wasn't my program. Looks like this time major number 244. So we're going to redo that mknod command. And if I cat hello, I get my hello world. This time I'm going to do echo test 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 to hello. Trying to change the permissions. That did it. And take a look. We get test 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 with a new line on the end of it. And if I cat hello, I get test test t, because I didn't change the size of the message. So one thing we can do is, since we know that the kernel was good right there, I can go back to my snapshot, revert to snapshot 7, and I don't even have to bother trying to unload anything. Same thing we did before, we make sure that we're on device number 244. Okay, and then echo hello, test, test, test again. Whoop. And this time it worked. It worked just like it was supposed to. And so now I can use this to create a device that holds a message for everyone who logs in. What we can do now is actually make this file, this hello driver, show up in the dev directory. So there's my dev hello, sudo mod 666 dev hello. So now it's readable to everybody. And remember, it's not that we're reading from a file, we're reading from a special file, a character special file. Every time I do I/O, I'm doing, in this file, I'm actually redirecting it to the character special driver handler in the kernel, and that's just directing it to one of the handlers that are registered as character devices. So let's go for the gold, I guess. Let's see if we can do the same thing to our Yocto, or sorry, our Pokey. We have our meta 7seg, our kernel recipe, our hello mod, our files, and our hello.c. Oh boy. So there's our simulator. So we'll try to rebuild our hello mod, and let's see what happens. Okay, so that worked. So I'll copy that .ko file, that kernel object. Here I am, I'm still running the QEMU simulator from video number 3. We'll do our Tftp Boot. Oops. Okay, definitely gone. We'll do our Tftp Boot. We're going to do the same thing we did before, so mknod dev hello c2440 and cat dev hello echo there it is. So this is a read-write kernel module. I'm going to make one more quick change in what we're doing over here. Okay, I spent some time with this last part trying to get things to work, and instead of going through the whole process, let me just give you an overview of what I had to do to make things happen. I wanted to be able to access the device driver and be able to send information that wasn't a read or a write. And to do that, we normally use a Unix function called an IO control, or ioctl. And I've modified the kernel driver that we've been working on in a couple of different key ways. The first is that I have the Linux ioctl.h file included. This gives me some definitions to things. Part of the ioctl requires that the major number is defined and can no longer be floating. So what I did is I picked one, but I wanted to make sure that there was nothing else living there. And so what I did is I looked at the file cat proc devices. This is a file that I can read that lists all of the registered devices. Now, I've already got my hello module loaded. That's the only thing that was at 202. You wouldn't want to pick a number that was used by something else. So I picked 202, and then I registered two different IO controls in my program. IO control 0 is going to set the mode to be 0, or mixed case. We'll explain that in a second. And IO control 1 is going to set uppercase. I then declared an integer variable static to my module called mode, and I modified my read function that whenever you read a message, if the mode is 0, that gives you the mixed case, is what we had before. If mode is not 0, then I'm going to look at every character I send to you, and if you're lowercase, I'm going to transliterate you to uppercase. If you're not lowercase letter, then I'm just going to send you the letter. So this mode 1 will always give me uppercase, mode 0 gives me whatever the message was. A little bit further down, I found, well, okay, a little bit further down, I had to handle the IO control method. And we're going to essentially look for the IO control set mixed that matches what we had declared up above in that pound define. And then I set my mode variable to be 0. If you do the IO control set upper, then I'm going to set my mode to equal to 1, and either way I'm going to just print out a kernel info so that we can see that it works. The other thing that I discovered is, I'm going to scroll down just a little bit. In the previous version of this module, I was not unregistering the character device driver, and so every time I did an RM mod, it left a residue behind, and it was slowly kind of messing up the kernel. So in addition to some of the other changes, always make sure that if you register something, you unregister something. It's kind of like a good idea. And then the last thing I wanted to point out was that the file operations, I needed to add an IO control handler. In some of the older Linux documentation, this is just listed as an IO control. In newer versions of the kernel, it's either a compat_IO control or an unlocked_IO control. I'm not going to get into the differences between them at this point. So the last change was I took out the dynamic major number registration when you register the character device. I turned it into register the device major number 202. The other thing I did is I wrote a little test program that can exercise this, and it includes the ioctl.h file for the user side, and we have the same pound defines here. So typically what you'd do is you'd put these into a .h file that's shared by the kernel module as well as the user code that's going to use it. But for now, I just hard-coded the set mixed and set upper to be major number 202, mode 0, 202, mode 1. Then, to use this, what I've done is I've written some code to open the device file for read and write. And then I'm going to take command line argument 1 and turn it to an integer, and if it's 0, I'm going to do an IO control of set mixed, and if it's a 1, I'm going to do an IO control of set upper, and I'm going to print the return code. And then the way this works, make sure it's loaded, we're going to set mode 0, and if I do a D message, we can see that IO control set mode 0 is the mode there. And if I do a sudo cat dev hello, hello world is all lowercase. If I do a test 1, this is going to do a set case upper. If I do my D message, I see the output from my code, IO control set mode 1. And now if I cat the device file, it's hello world all uppercase. I can also do my own message, test to dev hello. Oops, I need to modify the permissions of that file. And there again, it's all uppercase. If I go back to my test program here, set mode 0, and then I cat it, I get the original case of the message. So that demonstrates how to use IO controls to send information to the kernel module for maybe changing the mode of operation. I'm going to be using this in my next video to change the mode of the 7-segment display to between each of its 3 different modes, and then to be able to set things like the colon blink rate, things like that I want to be able to change without having to do reads and writes through the device driver. I think that should do it for this video. It's a little bit longer than I wanted it to be. Hopefully it shortens up when I edit it. In my next video, I'm going to actually put all of this stuff together. We're going to begin the actual 7-segment display driver. We're going to connect it up to the actual 7-segment display and push it out to the Z board. Thanks for watching and putting up with this long video.